The second category of intermolecular attractions is a dipole-dipole attraction. Remember, all compounds, all molecules, all atoms have London dispersion forces. This particular category, the second category, dipole-dipole, only occurs between polar to polar molecules. Polar molecules have a permanent dipole. London dispersions were a temporary induction. These are very permanent. Based on the polarity and the shape, we create these oppositely charged regions of a molecule. They are not temporary. They're based on molecular geometry. So we see regions of a molecule just based on its structure and electron density that have a region of positive and a region of negative. We can clearly see this region here being what's called a dipole-dipole attraction. The negative moment on one molecule being very strongly attracted to the positive moment on the other. Opposites attract in a polar molecule. The permanent dipole adds to the attractive forces between the molecules, thus even raising the boiling point and melting points even higher. Polar molecules boil much higher than a nonpolar molecule. The effect of dipole-dipole attractions on boiling and melting points. Thinking about a structure, CH2O, very equivalent molar masses. CH2O is formaldehyde. We used to use it as a preservative in biology class. Molar mass of 30.03. Ethane is C2H6, molar mass pretty close to the same, 30.07. Based on the formula weight alone, I wouldn't be able to predict what boiling point would be higher or lower. But if I look at the structure, I can clearly see the formaldehyde with its electron pairs up here on the oxygen, giving this region a little bit negative, these regions a little bit positive. The molecular geometry would be trigonal planar, 330. Very polar structure. Ethane is a non-polar molecule. There's nothing unique in this particular structure at all to make one area positive, one area negative. Based on the same molar mass, but one being polar, look at the difference in boiling point and melting point, significantly higher for the polar molecule than the nonpolar molecule. The dipole-dipole attraction creates a strong intermolecular attraction and thus increases the boiling and freezing points of our compounds. Here's the same idea. The molar mass of these compounds, very similar. However, the polarity of these molecules, very different. The nonpolar molecule, -42. A symmetrical molecule with oxygen at the center atom, a lone pair, but it's very symmetrical, -24. Oxygen versus nitrogen is what I'm seeing as the difference here. The electronegativity difference here is going to create a higher boiling point. We can clearly see the more polar the molecule, the more electronegative the molecule is, the higher the boiling point due to the dipole-dipole interactions. To determine if dipole-dipole attractions occur between CH2Cl molecules, I really just decide, is this a polar molecule? We started by finding the electronegativity value for carbon, 2.5. Each hydrogen was 2.1. Each chlorine, 3.0. We're trying to find if there's dipole-dipole attractions. We're trying to find if the bond would be polar. This formula for the Lewis dot structure takes the electronegativity difference into the shape of the molecule. Looking at the shape and just kind of going down here, this region on the molecule clearly shows a negative region. The molecule up here clearly shows a positive region. Without ever looking up electronegativity values, this particular structure clearly shows a region of negative and a region of positive. And as soon as I recognize it's not perfectly symmetrical, then I would have a polar molecule. And therefore, yes, every polar molecule would have a dipole-dipole interaction. If I replace these chlorines with hydrogens, perfectly symmetrical, no dipole-dipole, it's nonpolar. If I did a carbon tetrachloride and made all of the bonds going back to carbon, if they were all chlorines, perfectly symmetrical, it's nonpolar, so no dipole-dipole. But the original picture clearly showed an area of negative and an area of positive, making it a polar molecule, so yes, dipole-dipole. Predict the compound in each of the pair with the higher boiling point. CH2 with an F connected to a carbon, couple of H's and an F. Here we have something called a fluorine on the same carbon and a fluorine on the opposite carbon. So taking a look at the structure, I can just go from here to here. We can see clearly the answer that way. If the structure shows symmetry, I can literally flip this carbon and find it to be symmetrical. The area on the fluorine would be negative, but it's balanced by this area on the fluorine over here, which is also negative. It's symmetrical. But over on this side, I clearly see when the fluorine's on both sides, this region, the entire right side of this molecule will be negative. There's nothing unique over here, so it ends up to be positive. This molecule is more polar, therefore will have a higher boiling point. So the arrangement, notice down here the chlorines in the cis version of dichloroethane, if both chlorines are on the bottom versus one top, one bottom, this is a symmetrical molecule. The negative on this chlorine is being balanced down here. I can flip it and create the same molecule. Clearly, if they're on the same side, it's not balanced, positive and negative within the region. This molecule is more polar and therefore will boil at a higher temperature. Polar, nonpolar. Polar every time will have dispersion forces increasing the boiling point. Our third category of intermolecular attractions is called hydrogen bonding. When a very electronegative atom is bonded to a hydrogen, it strongly pulls the bonding electrons towards it. Hydrogen attracted to an oxygen, a nitrogen, or a fluorine. These are the three most electronegative elements. Because hydrogen has no other electrons, it's pulled away, and the nucleus becomes deshielded, unprotected if you don't like that word. So it's exposing the hydrogen proton. A little proton really is, this is a picture of a little hydrogen atom. It's one positive proton, one negative electron, and if I steal its electron, I'm exposing that positive proton. And it creates a very strong positive core, a positive attraction. That hydrogen bond is that exposed proton being very attracted to either a fluorine, a nitrogen, or an oxygen. The attracting of electron clouds from neighboring molecules creates the strongest attraction of all is a hydrogen bond. So hydrogen bonding, when hydrogen is directly exposed to a fluorine, oxygen, or nitrogen, the bonding atoms acquire relatively large partial charges, giving rise to strong dipole-dipole attractions. A hydrogen bond is between molecules, the hydrogen on one molecule being very strongly attracted to the fluorine on the other. The hydrogen on one molecule being very strongly attracted to the fluorine on the other. This here is the strongest intermolecular attraction known as hydrogen bonding. Hydrogen from one being attracted to either a fluorine or a nitrogen or an oxygen. That's it for hydrogen bonding. Those strong electronegative elements, F, O, or N. Hydrogen bonding exists in water and thus gives us one of the highest boiling points for a liquid at room temperature. The hydrogen on one molecule very strongly attracted to the oxygen on the other. This here is a hydrogen bond, this very strong intermolecular attraction. H from one molecule attracted to the O on the other. Here's yet another hydrogen bond. Hydrogen on one molecule attracted to the oxygen on